case where the crack width criteria is the case which determines the amount of reinforcement. And that steel fiber could help us to reduce the amount of traditional reinforcement because they can minimize the crack width. And this is what we are now investigating more in Europe, to use this combination. We're using a German guideline at COWI in Denmark for the design of steel fiber reinforced concrete, and we're using it because this German guideline is related to the Eurocode. It has the same chapter and so on. There are some other guidelines available, but we have not a standard for steel fiber in Europe yet. This is different to your country. And here, this is the design is similar to a normal design. We have a stress-strain relationship. The only difference is that we have here a tensile zone which we take into consideration in the design. We calculate with this tensile capacity. This is the big difference. And this tensile capacity will be determined at this 4-point bending test, which you can see here. And here, for example, this is the result of the calculation which we have done in COWI using this German guideline, and it's the moment MN interaction diagram, and here you can see the moment in relation to the crack width. This is the strain tensioning reaction here, which we can see. Now I'm coming to the door a little bit. This is not your focus.
Okay.
We can see this picture sometimes, or these are pictures from practice. We have this heavily corroding steel here on the left, and we have here steel fiber, which are panels exposed to a German motorway for over a lot of years, but still in good condition. Why is this? We have an increased durability of steel fiber reinforcement concrete, simple saying. The reason is that it can tolerate much higher chloride threshold values, up to 10 times higher. And there are some different reasons given here. The most important one, and Birk maybe can go on it later on if we have time, is that along a very small fiber there is the formation of a cathode and anode is almost impeded because we have only such a long fiber. So the probability of pitting corrosion is very, very small. In addition, fibers swim into the concrete. In contrast to a rebar, the rebar is we put into the concrete, and we know underneath a normal rebar we have often some segregation. There is in this contact zone between rebar and concrete we have a loss of adhesion or even voids and defects. But this does not happen with steel fiber because the steel fibers are swimming in the concrete. We have an excellent contact zone between steel fiber and concrete, and therefore we have an increased durability. This means only the fiber sticking out of the concrete will corrode. And this is very often called only an aesthetical problem. Even if some internal fibers would corrode, which we normally not believe, then the volume due to the rust is so small that there is no tension in the concrete that it can produce cracks. This is very important. And this has been verified by a lot of research projects in Europe. Two are mentioned here. This is a project where we use steel fibers. It's a heating tunnel in Copenhagen. It's a bore tunnel lining here, 4 kilometers long, and the diameter of the segmental lining is 5 meters. Here the alignment of the tunnel, interesting, it goes just underneath the palace of the Queen in Denmark. And inside this tunnel we have some pipes which carry steam and hot water. You can see here the tunnel underneath the Copenhagen city. Here you can see an earth pressure balance TBM which is used, and on the right side the steel fiber segments. Why did we use steel fiber in this case? So this is very interesting. The client requires 100, yes? We have very high temperature in the concrete. Due to this steam and the hot water, the concrete temperature during the normal operation is about 50 degrees overall the year. Due to this high temperature, we have an accelerated deterioration. There's a rule of thumb. If the temperature increased by 10 degrees, the deterioration, or each chemical process, will be twice as fast. In this case, we have a temperature about 50 degrees here. Normally, we have 10 degrees in the bore tunnel, in the earth, for the concrete. In that case, we have, due to this 4 times higher temperature, 6 times faster chloride ingress, which is very fast. In addition, we will have an accumulation of chlorides at the inside of the tunnel. This is because a bore tunnel is never watertight. There will be always some water coming in through the joints. I never saw a bore tunnel which is completely watertight. And therefore we have a risk of chloride accumulation inside here the tunnel, just beside the joints. Normally, if you would design with our normal design such a tunnel at this elevated temperature and with this chloride ingress, we would need a cover of 90, 100 millimeters due to this 50 degrees temperature. But this is impossible for a bore tunnel segment. We cannot have a cover here in the joints of about 100 millimeters. This is impossible, technically impossible. And therefore we had to find some other solutions. And one solution was to use stainless steel, here again, or to use steel fibers. And the contractor was a German contractor, Hochtief. He selected the use of steel fiber. The first thing is he selected it because it was less expensive. It saved him about 15% of the total costs. The other thing is it gives less damages at a segment. Because normally we have some damages if a tunnel bore machine erects the segments inside the tunnel. And it has a superior durability in case compared to traditional concrete. And please be aware, in a bore tunnel we normally need reinforcement only for the transport and for the handling. Afterwards, we do not need reinforcement because a bore tunnel is under compression during the normal operation. Why putting normal traditional reinforcement in, which only can corrode in some years, when it is not necessary? And this has to be verified. In our case, we didn't need steel fiber. We didn't need traditional reinforcement. Steel fiber was sufficient. Here, mix. It's typically about this one. We have about 35 kilo steel fiber per cubic meter concrete. This is the fiber class which we are operating in within the Eurocode, and not Eurocode, within our design guideline which we are using. The segments for this tunnel were produced in Germany, in East Berlin, a former big ready-mix construction company of East Germany, and the segments were transported via trucks to Denmark. And here is the load case which we investigated. Very often we have, during the installation of the segments, we have high pressure due to these forces from the tunnel bore machine. And we made some calculations to avoid here a cracking in this direction. And we used this German guideline, and we used a program in COBI FLEG, but you can use whatsoever sophisticated modeling program, and we found out that there is no cracking expected underneath this pressure. And therefore we only need, in this tunnel we only need steel fiber reinforced, nothing else. No traditional reinforcement at all. Here are some concrete tests. I will not go further in that. Here some pictures from the testing. This is the most important one. You have to measure the tensile capacity of a steel fiber reinforced concrete by this 4-point bending test. And the fiber class, according to our guideline, is defined. We have a fiber class 1.5, 0.6, and these values here giving just here in this diagram here. This is the definition of the fiber class according to our European standards. And we made a damage statistic, and it was not so surprising, but it was a positive surprise. We had less damages, less cracks at the tunnel line compared to traditional concrete. Out of over 2,000 elements, only 3 elements had cracks through the segments. And this was a partnering project, and you can see that almost all partners were happy. The client was very happy, the contractor, and the consultant. The next example is a warehouse where we used steel fiber reinforcement for a big foundation. It's a brewery, the Carlsberg Brewery in Denmark, which wants to build a fully automated warehouse with a computer-controlled stacker system. And here the foundation should be in steel fiber reinforced concrete without traditional reinforcement, only steel fiber reinforced concrete. And also in this case, the reason was because it was cheaper. The contractor got the job because he was cheaper compared to the traditional reinforced foundation. COWI made the calculations based on this German guideline, and we found out that the solution was 15% cheaper than the traditional reinforced concrete. And here's some impression from the calculations. We have the program available. If someone needs more information, please contact us. Here the testing. This is the beam testing. This is a washout test to determine how many fibers are into the concrete. And this other core sample for concrete density and fiber distribution testing. Our most recent project where we're using the steel fiber is this project in Abu Dhabi. It's actually a bore tunnel, but the bore tunnel will be used as a huge wastewater tunnel. It's for a new city of Abu Dhabi. And we have this part of the project at the moment. It's 16 kilometer long, 5 meter diameter, and there we're using a combination for the first time of steel fiber and traditional reinforced concrete. Interesting is, 80 years of service life, we have extreme high chlorides, 9% chlorides in the ground. I have never seen a project in my life where we had such high chlorides, and in addition, extreme high sulfate content in the soil, which we normally would never found in this part of the world. And here, in this case, we need some additional reinforcement along the radial joint because there the splitting forces are too high. Steel fiber is not sufficient. There we need some additional reinforcement. And this will be stainless steel. We also use steel fiber reinforcement for this shafts here and for a small cut-and-cover tunnel as alternative to a traditional design. And it's now up to the client to decide whether he wants steel fiber reinforcement or the traditional design. He has not yet decided. The last thing where we can use steel fiber is at bridges. You may see these pictures before. It's a bridge with some leaking cracks here. And the reason is that the traditional bridge insulation does not work anymore after, say, 20-25 years. The insulation is normally the two-layer of bitumen membrane, at least in Scandinavia. And so, as you can see here, what can we do? Why not using a sacrificial layer of steel fiber reinforced concrete instead of this waterproofing membrane on top of the structural concrete? as shown here. The sacrificial layer